What specific problem does the proposed method aim to solve in the context of transformer-based neural networks?
The proposed method aims to solve the problem of understanding the dependencies between the achievable performance, indicated by the pre-training loss, for transformer-based models and the model and data sizes during memorization. The method focuses on analyzing the behavior of transformer layers with associative memory, modeling the retrieval of stored patterns during training. It addresses the challenge of how larger models tend to encode and organize training data, leading to improved performance on downstream tasks. Additionally, the method aims to provide insights into the convergence dynamics of training loss during memorization, particularly in relation to model size and dataset quality. By incorporating associative memory models like the Hopfield network and the modern continuous Hopfield network, MCHN, the method offers a theoretical framework to understand the memorization process in transformer-based neural networks.
How does the proposed method work? Can you illustrate the methodology step by step based on the provided information?
The proposed method works by analyzing the performance of transformer-based language models as they memorize training samples. The methodology can be illustrated step by step as follows. 1. Modeling transformer layers with associative memory. The approach starts by modeling the behavior of transformer layers with associative memory, specifically using the Hopfield network and its modern continuous version, MCHN. These models are used to associate inputs with stored patterns and retrieve related memories. 2. Integrating feed-forward layers into attention layers. The method integrates feed-forward layers into attention layers, providing a unified view of the transformer structure. This integration facilitates analysis and understanding of the model's behavior. 3. Utilizing majorization-minimization, technique. The layered structure of transformer networks induces a sequential optimization process similar to the majorization-minimization technique. This technique constructs a global energy function tailored for the layered structure of the transformer network. 4. Analyzing cross-entropy loss. The method further delves into analyzing the cross-entropy loss of transformer networks, which measures the disparity between predicted probabilities and actual labels. The loss is formulated using the log partition function of the model's distribution. 5. Empirical evaluation. The methodology is empirically evaluated by examining the radius of stored patterns in a pre-trained GPT-2 medium model and training GPT-2 and vanilla transformer models on different datasets to analyze their cross-entropy losses. 6. Training and testing. The method involves training models on datasets of varying sizes and qualities, monitoring the training and test cross-entropy losses to understand the model's performance and generalization capabilities. 7. Comparative analysis. The proposed method compares the performance of models trained on different data sizes and datasets, highlighting the impact of model size, dataset quality, and training dynamics on the model's behavior and capabilities. In essence, the proposed method combines theoretical analysis with empirical evaluation to provide insights into the behavior and performance of transformer-based language models during the memorization of training samples.
What are the theoretical benefits of using the Hopfield network in the context of transformer-based models?
The theoretical benefits of using the Hopfield network in the context of transformer-based models lie in its ability to model associative memory, which allows for the storage and retrieval of patterns based on partial content. The Hopfield network, specifically the modern continuous Hopfield network, MCHN, provides a framework for understanding the attention mechanism in transformers by generalizing the model to handle continuous data inputs. This enables the transformer layers to associate inputs with stored patterns and retrieve related memories efficiently. Additionally, the Hopfield network helps in organizing memory based on the similarity of textual context, which is crucial for tasks such as text generation and question answering. The Hopfield network also aids in modeling the behavior of transformer layers with associative memory, enhancing the model's ability to store and recall information effectively during training and inference. Furthermore, the Hopfield network offers a structured approach to understanding how large language models encode and retrieve training data, leading to improved performance and generalization capabilities in transformer-based models.
How is the cross-entropy loss analyzed in the paper for transformer networks?
The cross-entropy loss in the paper for transformer networks is analyzed by considering the difference between predicted probabilities and actual labels, commonly used for training transformer models. The attention mechanism in the transformer includes a softmax operation that outputs a probability distribution. The cross-entropy loss is formulated using the log partition function of the model's distribution, reflecting how attention weights are allocated based on patterns. The loss is normalized by the size of the dataset. The paper discusses the cross-entropy loss on the test dataset and shows that it can be written as the negative log, likelihood computed over unbatched validation samples. The analysis includes a comparison of the cross-entropy loss with the energy function of the model, demonstrating that the loss is above a certain threshold, indicating the model's ability to memorize training samples. The paper also explores the relationship between the cross-entropy loss and the model's parameters and dataset size, providing insights into the optimal performance of transformer models during training.
What empirical results were obtained in the evaluation of the radius for the pre-trained GPT-2 medium model?
The empirical results obtained in the evaluation of the radius for the pre-trained GPT-2 medium model showed that the mean and median distances between the activation vectors and their nearest neighbors were approximately 20. This indicates that a typical B_I of pattern row caret I has a radius of 10. The histogram of the nearest neighbor distances for the output activations using different percentages of the output vectors, 25%, 50%, 75%, and 100%, displayed a mean and median distance of around 20, confirming the theoretical prediction that the radius is of the order of sqrt frac n 2 pi e equals 7.74. This analysis was based on the activation vectors of the last layer for predicting the next token in the GPT-2 model, demonstrating that the typical radius of the stored patterns in the model aligns with the theoretical expectations.
What insights were gained from training vanilla transformer models using the question formation dataset in the paper?
Training vanilla transformer models using the question formation dataset in the paper provided insights into the convergence dynamics of the models. The training losses for the vanilla transformers stabilized at a value of around 1, as predicted in the paper's proposition. This stabilization indicates that the models were able to effectively memorize the patterns in the training data, leading to a specific threshold of training loss. The results align with the theoretical framework proposed in the paper, showcasing the relationship between achievable performance, pre-training loss, and model and data sizes during memorization. Additionally, the training of vanilla transformer models on a small amount of high-quality data demonstrated the model's ability to generalize well and achieve similar performance to larger models trained on significantly more data. This highlights the importance of data quality and model size in achieving optimal performance in transformer-based models.